Okay, so sekarang kita akan start chapter 4 which is the detail design. Detail design ni sebenarnya senang je So that saya akan kongsikan slide. Tutup. Okay, chapter 4, detail design and the cost evaluation. Detail design ni sebenarnya which is banyak deal, more deal to the engineering drawing. So that saya tak adalah what we call emphasize on the engineering drawing because of that engineering drawing you have already learn in engineering drawing subject course during your first year of the study. But then in the course, but then in this chapter 4, I will emphasize on the how to select the suitable material to your product design. Means the material selection, and also how to calculate the selling price. The selling price, and then how much the profit that you will get. By doing the cost evaluation. This cost evaluation is I think is very important because from this cost evaluation we can determine how much the product cost, and then how much the selling the selling cost lah. How much you nak jual, and then how much the profit that you will get. Okay, this is the last part, which is the phase 3. The phase 4 and phase 5 kita we are not cover. So that the phase 3 we will cover on the detail design about the engine drawing. But then isolatekan sikit lah about material selection process. And then the bill of in materials. I think bill of material pun is a part of the engineering drawing. I think that one is you have already known. And then the cost evaluation. The important one is the cost evaluation. So that the first part is material selection process. Why the material selection process is important? Because material selection in the product design is a part of the design process that determine appropriate materials for design product by considering related design criteria. And you need to find the Okay, this material selection, you need by determining the appropriate material for the product, because not only just you select any material, but then that material we need to consider the criteria of the product. Maksudnya contoh dia such as how about the manufacturing processes, availability, the environment, the cost, and then function, shape, content, etc. It means that if you want to if your product is the application is in elevated temperature, in high temperature, maybe dalam furnace ke apa kan. So that we need to select that material that material that can sustain at high temperature. Contoh mungkin you tak boleh select polymer as a material for your product. Maybe you need to select polymer material temperature rendah kan. Maybe you need to select the ceramic type of the material, because the melting temperature of the ceramic is more than 1000. That is for example lah. And then the material selection relies on a set of the objective, requirement and other constraint. Maksudnya material selection tadi dia terbahagi kepada tiga komponen utama, which is we want to know what is the objective of your product. Macam tadi lah saya cakap, mungkin you punya produk you nak buat kuat tetapi ringan. So that you kena carilah material yang kuat tetapi ringan, and then the requirement dia mungkin tadi application dia, requirement dia perlu pada high temperature. So that you kena carilah material yang kuat, ringan, high temperature, and then mungkin dia ada constraint lah. Mungkin constraint dia kata mungkin dia tak nak metal, dia nak polymer, dia nak jenis yang selain daripada metal. Contoh nanti kita tengoklah dia punya detail. And then inappropriate or improper decision can be disastrous from both economic and safety perspective. Of course lah, bila you wrong decision yang you buat untuk you select the suitable material, so that one akan cost ekonomi, maksudnya cost akan bertambah lah sebab you nak kena select balik material yang lain. And then dia punya safety lah, macam tadi saya cakap lah, kalau kata produk tu untuk high temperature tapi you select that material yang tak boleh sustain at high temperature, so that it safety perspective. Okay, yang ni pula, ni pun saya tak nak sentuh banyak sebab you dah belajar dalam engineering material. Basically, we have 3 basics of the engineering material. We call the metal. Semua tahulah metal is strong, and then ductile, high thermal and electrical conductivity, opaque, and also reflective. And then the ceramic, covalent bonding, soft, ductile, low strength, low density, thermal and electrical insulator, optically transparent or transparent. Sorry, dia sebenarnya ceramik dia tak semua ductile. Kebanyakan ceramik adalah apa satu lagi tu, brittle. And then dia punya hardness tinggi. Ceramik ni contohnya you punya, itulah apa kata, you punya tile. You punya tile kat rumah tu ataupun pasu bunga. And then the polymer, ionic bonding, refractory, compound of metallic and non-metallic elements. And then the brittle, glassy, elastic, and then non-conducting. Maksudnya polymer dia adalah insulators. And then other type of engineering material, composite. Composite, which is the mix of 2 or more materials. And then ni semua composite lah ni. CFRP, carbon fiber reinforced polymer, GFRP, graphite fiber reinforced polymer, wood, aramide, semiconductor, biomaterial, and then the smart material. Smart material contohnya shape memory alloy lah, ataupun piezoelectric ceramic, magneto-restrictive material. Shape memory alloy maksudnya you buat macam mana pun dia boleh ingat dia punya bentuk asal dia. Contoh bentuk asal dia bulat, and then kalau you gunakan thermal, you panaskan, mungkin dia dah berubah, tapi lepas dia sejuk, dia balik kepada bentuk bulat. That one we call the smart materials. Okay, this is apa orang kata the kingdom of engineering material lah. Kita ada metal, kita ada apa orang kata class of metal, kita ada class of polymer, kita ada class of ceramic, and then kita ada class of composite. Kalau ceramic ni kebanyakannya dia ada macam ni lah, alumina, silikon karbida dalam bahasa Melayu lah. Silikon nitrida, contohlah dia ada macam tu. Okay, this is the the selection criteria of engineering material. Macam tadi lah saya cakap the engineering material, untuk selection of the engineering material kita tak boleh just select random. We need to have the criteria. The first criteria is the material properties. This material properties is the most important. Yang kita perlu select, yang kita perlu adalah dalam kriteria untuk kita select the engineering materials. And then define specific characteristic of material, form a basic predicting the behavior of the material. Ini semua maksud dia, ini semua adalah determination of the material properties lah. And then this is the contoh important properties of the material, which is the mechanical properties. Macam biasalah, stresses semua tu kan, von Mises. And then the thermal, chemical, and then electrical, radiation. This is the important properties of the material. And then the second one is the performance requirement. The material of which a part is composed of must withstand the external environment and perform the part function without failure. For example, the material of a furnace wall must withstand at the high temperature. Ini contohlah performance requirement dia. Yang tadi material properties. And then dia punya dia performance requirement. And then material reliability. The reliability is a degree of probability that the product and the material is made of will remain stable enough to function in service for the intended life of the product without failure. Both dia punya keywords adalah without failure. And then a material in a given application must be reliable. And then number 4 adalah safety. Ni biasanya berkait dengan safety lah. Contoh, a material must safety perform its function. Contohnya, the failure of the product made out of it may be catastrophic in certain situations, such as in airplane and high pressure system. Safety tu kita kena ni lah. Maksudnya airplane ni dia kena tahan suhu lah. Maksudnya kalau bodi kapal terbang tu kena tahan suhu yang sejuk sebab dekat atas tu sejuk. Okay. And then the next one is the physical attributes. The physical attributes such as configuration, size, weight and appearance sometimes also serve as a functional requirement. And then environmental condition, the environment in which a product operates strongly influence services performance. And then the humidity, water, chemical can cause corrosion and subsequent failure of the material. Ni environmental condition ni contoh dalam laut. Kita nak letak contoh kapal selam lah, nak letak dalam laut, kita kena ambil material yang boleh sustain the corrosion. And then disposability ataupun recyclability should be disposal and reusable through rework and modification. And then ni mungkin salah satu juga kriteria, you kena cari material yang boleh recycle ataupun biodegradable. Sebab macam kita tak nak kita tak nak waste waste management tu kita waste management tu lah kita kena kawal. Maksudnya kita tak boleh buang. Maksudnya kalau you dah tak nak material tu, you nak buang, you tak boleh, kalau dia tak boleh recycle, you terpaksa kena ada management step lah untuk buang that material. Sebab dia tak biodegradable. Maksudnya you tak boleh buang dekat land je. Kalau buang kat land, dia tak biodegradable pun. Contoh plastik kan, tapi plastik sekarang dah biodegradable. So that you kena pilih material yang boleh disposal dan juga boleh recyclable. Boleh recycle lah. And then availability and economy. Ini pun penting juga. Maksudnya kalau you pilih material tu memang tak ada kat Malaysia, there is no point. So that you kena pilih yang material yang available di Malaysia ataupun yang kalau pun tak available di Malaysia, maksudnya you boleh dapat somewhere. And then of course the economy. Kita tak nak pilih material yang terlalu mahal. Contoh takkan you nak pilih titanium untuk just a product, apa orang kata, just kursi duduk je you nak pilih titanium. No apa kata? No pointless, no useless. Okay. Okay, this is the process of the material selection. We have 5 steps. The first step, you need to define the function. What does the component do? Maksudnya, any engineering component has one or more function. Maksudnya, you punya produk tu, functionnya adalah untuk apa? Adakah untuk support load? Sekejap ada orang call. Okay, sorry Okay. So that kita ada 5 step. The first step, define the function. Maksudnya you punya contoh, you nak buat produk you adalah kerusi. So that, of course, the function of the kerusi need to support the load of the human. Maksudnya, you nak support load lah. Ataupun pressure. Tapi tak adalah untuk nak transmit heat. Sebab ni nak ini ke kerusi kan. So that function dia lebih kepada load. And then the step 2, you need to define the objective. What is the maximize and minimize? The designer has an objective to make, contoh dia, to make it as cheap as possible, or as light as possible, or as safe as possible, or some combination of this. Maksudnya, bila you dah tahu contoh kerusi tadi, you nak load dia punya function dia untuk support load, and then you nak tahu your objective you untuk produk, untuk you punya kerusi tadi, mungkin you nak yang murah, ataupun you nak yang ringan, ataupun you nak yang safe lah. Safe maksudnya tak balik ke apa kan. Maksudnya kalau terlalu ringan kan terjatuh lah pula. So that, mungkin ataupun combination. You nak ringan dan juga murah, ataupun mungkin you nak safe dan juga murah. Contoh. And then you define the constraint. Bila you dah tahu dia punya function, you dah tahu dia punya objective, you define dia punya constraint, what specific requirement must be met. Contoh, the objective must be achieved subject to constraint. Maksudnya objektif yang ni tadi, you nak maximize ataupun you nak minimize, adalah subject to the constraint. This one. For example, the dimension of fix. Maksudnya, dia punya contoh constraint, you nak dimension, katalah, you tak nak terlalu besar. So that you dah tetapkanlah berapa meter you nak kerusi tu panjang, ataupun berapa lebar, berapa tinggi. And then the component must carry the given load without failure. This is apa kata yang common lah. Kita komponen tak nak failure, maksudnya apa kata safety factor tu kena tinggi, maksudnya lebih daripada 1, and it should function in a certain temperature range. Contohlah, tapi kalau you nak design kerusi, tak adalah you nak function certain temperature range. Contoh kalau katalah you nak you nak buat katalah dekat refinery punya material kan, so that one kena ada elevated pada certain temperature yang dia perlu ada. And then the select best solution, lepas dia dah tahu function, objective, constraint, you select the best solution based on the highest priority ranking score, summarize the material that meet the requirement. Potential material are ranked following the objective in order to select the best material or use the push method. Contoh dia, from the list of possible material. Okay, contoh bila you dah ada function, you dah ada objective, dah ada constraint, mula-mula contohlah, ada 10 material. Lepas tu, you dah, daripada 10 material tu, you dah filter. Maksudnya you filter up this 10 material adalah mungkin daripada, you dah tengok daripada function dia, daripada objektif dan juga constraint. Antara ketiga-tiga kriteria, requirement ni tadi, bila you dah ni, daripada 10 material tadi, mungkin 5 saja material yang meet all the function, all the objective and all the constraint. Mungkin 5 saja. And then daripada 5 ni memang dia dah filter out lah. Memang 5 ni dah finalize dah. Memang dia meet all the requirement yang you nak tadi. So daripada 5 ni macam mana you nak pilih the best? So dia ada 2 cara. The first cara daripada ni adalah you tengok pada ranking. Yang mana you rankingkan yang first. So you pilih lah. Tapi ranking tu you kena determine sendirilah ranking dia. Contoh, you berbalik-balik kepada objektif tadi. Mungkin dia kata, for example, choose the material that the lightest and cheapest. Itu adalah mungkin daripada 5 tadi, mungkin yang material A adalah yang paling lightest dan juga cheapest. So that you rankingkan ni based kepada objektif tadi. Mungkin objektif you kata tadi, you nak paling ringan dan juga paling murah. So that you rankingkan lah yang 5 ni tadi. Mungkin material A yang paling ringan dan juga murah. So that you pilihlah A. Ataupun yang keduanya, you boleh menggunakan push method yang you dah belajar dalam konsep design. You buat push method antara 5 ni tadi, menggunakan datum biasanya adalah material yang the existing material. So that you rankingkan menggunakan push method. Dia ada 2 cara lah untuk cari the best solution. And then the step 5, identify require processing. Bila you dah pilih that material, you kena identify lah apakah proses yang diperlukan. Contoh, kalau kata you nak buat kursi, you nak guna proses apa? Mungkin sewing ke ataupun injection molding ke, you can decide lah for that particular material yang you dah pilih. Okay. Okay, this is the method for the material selection. Sebenarnya kita untuk yang untuk step-step 1, 2, 3 ni tadi, 1, 2, 3, 4 ni tadi, sebenarnya menggunakan HB chart. Dalam HB chart ni, HB ni nama orang lah. HB chart ni sebenarnya dia adalah combination of all material in the world, dalam dunia kita ni, semua material yang ada dalam chart ni. Dia ada banyak lah. Dia ada young modular versus density, dia ada strength versus density, dia ada wear versus density, dia ada price versus density. Macam-macam lah, dia tak semestinya density. Mungkin dia ada price versus young modulus. Dia berbagai-bagai graf dia ada. Tapi ini adalah salah satu contoh lah. Young modulus versus density yang biasa, mechanical, engineer refer. Biasanya HV chart ni kita boleh buat dua. Satu guna manual style, satu lagi menggunakan software iaitu CES, Cambridge Engineering Selector. So that untuk you punya projek ni, saya cadangkan advice you guna CES, Cambridge Engineering Selector. Sebab Cambridge Engineering Selector ni dekat FKM kita memang ada beli. Cuma sebab you dekat rumah, benda tu dekat lab, so that saya cadangkan you try lah cari open source punya ataupun yang yang pirate ke apa kan. Tapi janganlah you sebut benda tu pirate. Cuma dekat FKM ni, CES kita adalah CES 2013. So that saya advice sama ada you guna manual ataupun you guna CES software. You carilah mana-mana pun CES software ni. Dia ada je sebenarnya. So that ataupun you menggunakan huge decision matrix. Maksudnya kalau katalah you tak nak guna HB chart ni, you boleh guna huge decision matrix. But then this huge decision matrix, ni dirasakan aktiviti 1, 2, 3, 4 ni adalah can be determined from the list of possible material preliminarily selected from the HB chart and that meet all the requirements. Maksudnya whatever it is, you kena refer pada HB chart. Huge method ni selepas you select daripada HB chart. Mungkin, okay, contoh ni adalah line-line ni kan. Line nanti kita akan tengok. Tapi sebenarnya ini adalah guideline for minimum mass design sebab dia density. Nanti kita akan tengok satu video macam mana dia nak select the suitable material from the HB chart. Nanti kita kejap lagi kita tengok. Ini sebenarnya benda-benda ni sebenarnya ini nama dia matrix performance index. Sebenarnya performance index ni you dah belajar dalam solid mechanics. Which is kalau katalah bentuk dia rod, apa performance index dia. And then kalau katalah bentuk dia T-square, apakah square, apakah dia punya performance index dia. Yang tu you kena, itu sebenarnya you dah belajar dalam solid mechanics. So saya takkan cover dalam ni. So kejap lagi kita akan tengok macam mana cara dia select material menggunakan HB chart. So I nak you tumpukan pada video ni. Dengar tak video tadi?
Tak dengar ke?
Tak dengar kejap Mana saya nak buat ni Kat rumah buat boleh. Di sini tak boleh. Oh, kejap.
First of all, we're going to have upward forces at the rear wheel and the front wheel. We're going to have the mass or the weight of the user acting down. And the user is also going to be applying forces at the pedal. Up to this point, we've been looking at material properties in isolation, but in this example, we're going to look at two properties that are connected, and I'll explain this a bit further as we go along. First of all, let's consider the bike frame that's shown, and let's consider the forces that are likely to be acting on this bike frame. First of all, we're going to have upward forces at the rear wheel and the front wheel. We're going to have the mass or the weight of the user acting down, and the user is also going to be applying forces at the pedals. Now, the simplest way to evaluate this is to consider it as a pin-jointed framework. And what that means is that each of these trusses that we've drawn can only exert either a compressive or tensile force. So they can only apply linear forces, each of these trusses. So when it comes to evaluating this bike frame, what we're actually considering is direct loading. Now, first of all, we're going to want this framework to be strong. We're going to want it to have a high strength. So we want high strength. And if you recall, the symbol for strength or for stress is sigma. So we need it to have high strength. The other thing that we're going to want is we're going to want this frame to be stiff. Because it's being subjected to a number of forces, the last thing we want is for this frame to twist. So we want high stiffness. And if you recall, we said that means it needs a high elastic modulus. Now, the third factor that we're going to consider is the mass or the density of the material that's used. If we were looking to produce a high performance bicycle, then we would want the frame to be light to improve performance. So we want So in actual fact, we're going to consider two things. We're going to consider strength per unit mass. You've probably heard of strength to weight ratios before. And we're also going to consider stiffness per unit mass. So next I'm going to introduce you to something called the materials index. And we're going to look at this in very basic detail because material indices are actually beyond the scope of this unit. But I'm going to introduce them to help you to evaluate different materials. So first of all, we need a formula for the mass of this bike frame. And mass is density times volume. Density times volume of the framework. Now, if we assume that this framework is of equal cross-section throughout, then what we can say is that the mass of that framework is the density of the material used times the cross-sectional area of the tubing times the overall length of the tubing. We're making some assumptions there because it's actually unlikely that the cross-section throughout that frame would be equal. So we'll call that formula 1. And another formula that we're interested in is the formula for stress or for strength. Stress is the applied force over the area. Now what we want to do is combine these two equations because at the moment we have a formula that involves stress and we have a formula that involves density, but we want a combined formula or a way of evaluating strength over density or stress over density. So what I'm going to do is I'm going to rearrange equation 1 and I'm going to rearrange it to make A the subject. And the reason I'm going to do that is because both of our equations contain A. So I'm going to take equation 1. First of all, I'm going to rewrite it. Mass equals, instead of density area length, I'm going to write density length area. And the reason I'm doing that is because it's easier then to rearrange. We can see that we need to divide each side by density times length. We'll be left with area equals mass over density times length. Now I'm going to substitute that formula into equation 2. So we can write 1 into 2. And I'm going to rewrite that as stress equals force divided by area. Well, if area is going on the bottom, or M over rho L is going on the bottom, then M will go on the bottom and rho L will actually go on the top. But if you recall, we said that we wanted to minimize the mass. So what I'm going to do is rearrange that now to get mass on its own. And the way I do that is by timesing each side by M and then dividing each side by sigma. So I'll get M equals F rho L over sigma. I'm going to rewrite that because I want to group density and sigma together. So instead I'm going to write F L times rho over sigma. So finally, if I want to minimize M, I need to minimize rho over sigma. The reason being is the force is going to be a constant and the length of the tube is going to be a constant. The only two parameters there that are affected by the material is the density and the strength of the material. Now, if I want to minimize the mass by minimizing rho over sigma, then that's exactly the same as saying I'm minimizing the mass by maximizing sigma over rho. I'm just inverting that fraction. So what we're looking to do in this example is we're looking to maximize sigma over rho. It is worth mentioning that the indices for each of those, sigma is to the power 1 and density is also to the power 1. And that's going to influence how we use the chart. The reason why I mention this is sometimes when you go through this process, one of these powers or one of these indices may end up being 2 or 3. And this is why using material indices can sometimes become a little bit complicated. We have a relatively straightforward example because we have direct loading, but if you had bending or torsion as an example, then you would have to reconsider the material indices. But that's sufficient as an introduction. Let's look at how this impacts on our graph. So here we have a graph of strength against density. And once again, this has been produced using CES EduPack 2017 by Granta Design Limited. And recall that our goal here is to maximize sigma over rho, strength over density. When we looked at the material indice, we found that we would have a material indice of 1 because we have direct loading. Well, a material indice of 1 is represented on this graph by a gradient of 1, a line with a gradient of 1. So let's look at what that means. When we go from, on our y-axis, 10 to 100, we've increased tenfold. And when we go on our x-axis, from 10 to 100, we've increased tenfold. Therefore, any line that connects the two corners of any of these squares is going to be a gradient of 1. So we could draw a line there, it would be a gradient of 1. We could draw a line here, corner to corner, and it would have a gradient of 1. And let's begin by drawing a line here. Now what this means is every material on this line would have an equivalent strength to weight or strength to density ratio. So all of these materials in effect would perform equally for strength over mass or strength over density. Now if we want to maximize that ratio, we need to move that line with gradient 1 upwards for maximizing. So let's draw a second line. And this time we'll cross the corners of the next box like so. What you notice now is that there's very few materials still in the running. We can see that carbon fibre reinforced polymer, here as an example, would perform very similar to diamond in terms of strength to weight ratio. But we can see various other materials, such as our steels are underperforming, and also our aluminium alloys here are underperforming. Now obviously we would rule out diamond, it's very expensive and it's very difficult to form, so really the material that's left in terms of strength to weight ratio is the composite material carbon fibre reinforced polymer. So for a high performance bike we're probably looking at carbon fibre reinforced polymer as our material. We're going to look at another chart, and this time we're going to look at elastic modulus against density. And we're not going to go through the process of determining the indice again, but the indice will once again be 1 as we have direct loading. So this is the final graph that we're going to look at, and again it's been produced using the CES EduPack 2017. And what we have this time is our Young's modulus, or our stiffness, on the y-axis, and our density on the x-axis. We're looking for a material with high stiffness, low density, or we're trying to maximize the relationship of E over rho, elastic modulus over density. Now each of these are going to be to the power of 1. So once again, we need a line with gradient 1. Lines with gradient 1 connect the corners of these rectangles. So we can sketch a line on here, and all of the materials that sit on that line would perform equally in terms of stiffness over density. Because we want to maximize that relationship again, we need to move this line upwards in this direction. And we're looking for the material or materials that perform best in terms of that ratio. So as we move this in that direction, what we notice is we get to a point where there's very few materials remaining. Once again, I'm going to overlap our carbon fibre reinforced polymer. So let's just add a line here. So overlapping our carbon fibre reinforced polymer there, we can see very few materials that are still in the running. And in fact, the only other materials are ceramics. Now there's a number of different problems with ceramics. They're difficult to form, but they're also relatively brittle. So once again, if we're trying to optimize the design of our bike frame, we're only really left with one possible material, and that's the composite material, carbon fibre reinforced polymer. So let's summarize. So in order to optimize the design of our bike frame, we wanted to maximize stress and we wanted to maximize elastic modulus over density. When we looked at stress over density, we considered a number of different materials. We considered carbon fibre reinforced polymer. We also discussed alloys of aluminium. And we also discussed steel. Now the reasons why we discussed aluminium alloys and steel is because bike frames are often also made from those materials. The cheaper bikes tend to be made from steel, then we have aluminium alloys, and the most expensive bikes tend to be made from carbon fibre reinforced polymer. Now when we evaluated the strength per unit density, what we found was that carbon fibre reinforced polymer outperformed both the aluminium alloys and the steel. And then we did a second evaluation where we looked at the stiffness per unit density, and once again we found that the carbon fibre reinforced polymer outperformed the other two materials. So why then are the cheapest bikes made from steel? Once again, it's going to come down to the ease of manufacture and hence the cost. So the materials are cheaper and they're easier to manufacture. When we consider aluminium alloys, the reason why aluminium alloys are used is because they have low density. They tend to be relatively strong, but also very light. But by far the strongest, stiffest and lightest materials are the carbon fibre reinforced polymers. The cost of those is greater because the manufacturing process is much more complex. And we'll look at various different manufacturing processes in a later tutorial.
Okey, ni cara dia tunjuk dalam HB ni.
Pack 26. One of these indices may end up being 2 or 3.
Inilah yang saya cakap tadi.
This is why using material indices can sometimes become a little bit complicated. We have a relatively straightforward.
Jadi saya tak akan ulang lah. Okay, so, saya just nak emphasizekan dekat sini yang mana tadi. Okay, macam mana dia dapat line ni Okay, sebenarnya kalau you tengok daripada material index ni, okay, dengar Okay.
Here we have a graph of strength against density.
Dengar tak?
Dengar.
Okay. Jadi kalau awak tengok daripada yang ni, okay, yang ni tadi kan.
The reason why I mention this is sometimes when you go through this process, one of these powers or one of these indices may end up being 2 or 3.
ini sebenarnya
and this is why using material indices can sometimes become a little bit
rho bagi
complicated.
alpha,
We have a relatively
alpha bagi rho.
straightforward
Ini apa
example
ni rho
because we
ni
have
alpha.
direct loading, but if you
M
had
rendah
bending or
alpha bagi rho
torsion as
ni
the
adalah
example,
sebenarnya
then you would have to reconsider the material indices. But that's sufficient as an
y
introduction. Let's look at how
equal
this
to
impacts on our graph.
mx tambah
So
c
here
tu.
we have a graph of
Ni. Yang mana ni alpha ni, ini adalah ni. Ini adalah alpha bagi rho. Yang mana dalam kes ni C ni adalah kosong lah. Tak ada lah. That's why bila dia lukis tu tadi, bila dia lukis line ni, kalau awak perasan, kan? Line ni kalau
these
kita
materials in
linekan
effect
ni
would
ke
perform
sini,
equally for strength over
dia akan
mass or strength over
kata
density.
dia adalah
Now,
kecerunan
if
ni
we
lah.
want to
Kecerunan dalam benda
maximize
ni.
that ratio, we
And
need
then
to
dia
move that
punya
line with gradient
ni
1
kita panggil apa
upwards
C
for
ni?
maximizing.
Kita panggil
So
dekat
let's
dia
draw a
punya ni kan,
second
dekat dia
line.
punya Y ni. Kalau awak tengok ni sebab bukan kosong kan. So that sebenarnya kalau kita
And this
extrapolate kan,
time,
dia
across
adalah
the corners of the next box,
dia
like
sebenarnya
so.
macam ni lah. Dia daripada kosong. Sebab ni
What you
adalah kosong,
notice
C ni
now
kosong.
is that there's very few
Tapi dekat sini
materials
dia
still
nampaklah
in the
dekat
running.
satu ni
We
sebab
can see that
dekat sini bukan
carbon
kosong.
fiber reinforced polymer,
Kalau sini kosong, dia
here
kalau
as an
extrapolate,
example,
dia
would
kosong-kosong.
perform
Tapi
very
kalau katalah
similar
Y
to
equal
diamond
to,
in terms of
katalah
strength to weight
MX,
ratio.
katalah C ni,
But we can see
tambah
various
C
other
ni adalah 1.
materials,
Maksudnya,
such as our
yang ni bisa jadi
steels
macam
are
ni lah. Nanti graf
underperforming,
dia akan jadi macam
and
ni.
also our aluminium alloys
Biasanya kita
here
menggunakan
are
graf
underperforming.
block. So then,
Now, obviously, we would
anything,
rule out diamond. It's very
apa kata,
expensive and it's very difficult to
material
form.
yang atas
So really,
daripada
the
garisan
material
ni
that's left in terms of strength to weight
adalah yang
ratio
possible material
is
lah
the composite
untuk
material carbon
you punya
fiber
produk tu
reinforced
lah.
polymer.
Dalam ni bicycle ni
So
dia
for a
nak
high
strength tinggi,
performance
density
bike, we're
rendah,
probably
kan?
looking at carbon
So then,
fiber reinforced
anything
polymer
yang
as our
atas
material.
garisan ni adalah possible
We're going to look
material.
at another chart,
Maksudnya
and this
dalam
time
ni
we're going to
dia
look at elastic modulus
carbon,
against density.
alloy, steel ataupun
And we're not going to go
diamond.
through the
Yang mana
process
bawah
of
daripada
determining
garisan
the
ni
indice again,
bukan
but the indice will once
tak meet
again be
all the
1
requirements
as we
lah.
have direct
Maksudnya
loading.
atas garisan ni dia meet all the requirements.
So this is the final graph that we're going to
Contohlah.
look at, and
And then
again it's been
juga
produced
untuk
using the
yang
CES
modulus dan juga
EduPack
density.
2017. And what we have this time is our Young's modulus, or our...
So this one adalah tadi secara manual. So yang ni dia tunjukkan secara macam mana nak buat menggunakan CS software. This is the apa kata the interface untuk CS software lah. So then you try tengok macam mana dia buat ni. Sebenarnya senang je CS software ni. You klik terus dapat.
Hello, we go to a very brief tutorial on how to use CES Cambridge Engineering Selector EduPack 2017. We're gonna do these tasks. We're gonna explore at epoxy at different level 1 and level 2 of the software. We want to create Young's modulus and density chart and the rest of the tasks that we do. The first step is to open CES EduPack 2017. As you can see, when the software opens, the first thing that pops up is the databases. You have different levels of the information provided by the software. Level 1, of course, the simplest one, and then we have more material level 2 and level 3. And if we want to focus only on the elements, then we can use this tab. So I start from level 1, and the first task is to, as you can see here, to explore epoxy. So as you can see in the left hand side, we can browse through different materials. Of course, epoxy we know is a polymer, so I click on the polymer. We have thermoplastic, thermosets, and we have only 3 types of thermosets here. Epoxy, so I click on epoxy, and then I have the general description of the epoxy composition and other type of physical and mechanical properties, and the rest of the properties of epoxy listed here. So we can use this information. Even we have information about the price of this type of material in general. You know, in general we have many types of epoxies, so this is taking epoxies in general into consideration. If I want to look at the same properties in level 2, what I do, I just go to File, Change Database, and instead of level 1, I change to level 2. Then I'm introduced to this page. Again, I have all materials. I can explore it from here or from the left hand side. So I click on polymers again, and thermosets similar to what I did here, and I have epoxies. Of course, I'm expecting to see more information, mechanical, thermal, physical information listed here, and here I have compared them in this picture. The right hand side shows the general properties listed for epoxy here based on level 1 information, and the left hand side is based on level 2. Of course, you see more information, more mechanical properties, thermal properties, so on so forth is listed under level 2, and I'm not finished here. Still the list is continuing. The next step, I want to use CS software and list or create the chart of Young's modulus of the different materials in the world versus their density chart. So what I do, I just go to the software and select chart here, click on the chart. I have three options. The first one is the chart. We can make limit, add limit, or select from three of materials. So I click on chart. I'm provided with y-axis option and x-axis option. So if I go back to the task explanation, I have to have Young's modulus, say, in y-axis and density and x-axis. So I go back there, and y-axis I have Young's modulus. So I go all the way down this attribute list and select y modulus. On the x-axis, so I leave it as logarithmic. I can choose other types of format, linear, so on and so forth. For the x-axis, I go the attributes and I select density from this alphabetical attribute, and then when I press OK, now I have the list of all these materials. Of course, it's level 1, which are listed here, and I have a chart of Young's modulus versus density. So I created that one, level 1. Of course, if I go to level 2, of course, you will see there are more materials. Let's change the database from level 1 to level 2. Do you want to apply the yes? And of course, there will be more. Maybe it's not very clear in this picture. I can show the family envelopes by clicking on this button. I have family of foams, natural materials, elastomers, polymers. So left click and drag. Ceramics, composites, technical ceramics, metals and alloys. So I can easily select different envelopes of the material. As you see in this chart in lower left, we have those type of materials that they have very low Young's modulus, very low density. On the very far right top corner, I have those materials that they have high Young's modulus, high stiffness, and high density. Now let's go back to the task. We want to use box selection for those materials that have Young's modulus bigger than 100 gigapascal and density smaller than 5,000 kilogram per meter cube. So what I do, I click on the box selection here, click, and look at, of course, I want to have it more than 100. So this is 100 all along this line, and here 5,000, so 1,000, 2,000, 3,000, 4,000, 5,000, so approximately here. So I can say everything inside this material satisfy this condition, the limits that we just defined based on this box selection. And if I want to hide the failed materials, I can click this one and they are all gone. As you can see, The family envelopes is shown here, but they are turned gray, which means they did not pass these limits. So that's one way of adding limits and a step to find our desired material that they have passed certain criteria. Of course, we can look at other properties like price.
Okay, kita sambung tempat dia.
Hello, we go to a very brief tutorial on how to use CES Cambridge Engineering Selector EduPack 2017. We're gonna do these soft. Okay, as you can see, when I add this limiting condition in the box, the list of materials that have been here, some of them are gone. These materials are gone, and then we have a shorter list to select from. Now we want to do the same thing and using limits option that we have in the software and select those type of material that they have the same conditions. So there is another approach. Let's go back to the software. So in order to remove and delete this box and the type of material, I can select delete lines or boxes, and you see we go back to our initial place. So what I do this time, here instead of chart, I click on limit. I have lots of properties that I can focus on them. The properties that I'm interested in, one of them is density. Let's go back to the part. Yes, density should be maximum 5,000. So I just select 5,000. You see we have also option for price. So if price is of course it's always a concern in design, so we can use some limits here. So now I'm only concerned about density, and the other limiting condition is E, Young's modulus bigger than 100 megapascals. So I go to mechanical properties, and I want this to be minimum 100 gigapascal. So when I do this, I apply it. As soon as I apply it, if I go back to this stage, I see only few type of materials are left. Okay, I just noticed that this is a different answer, because in the box selection, unfortunately, or I didn't select those material that are below a specific 5,000 kilogram. I selected those who are above it, so that's why I had this sort of selection. So now the selection is shifted. This is the exact, and I think more precise and easier way to add the limits. So the limits that I have, one of them is maximum the density of 5,000 kilogram per meter cube, and Young's modulus of 100 gigapascal. Say, of course, if I, instead of maximum, this is going to be the minimum, I should see apply something similar to what I saw in the previous selection using the box selection. So this is how we can use limiting. Of course, there are lots of options that we can go over them, and then add limit to our selection by minimum of a value or maximum of a property. Sometimes we need to define or add a material index in our design, and it's actually it can be shown by a line, a straight line in the chart. We will discuss it in the next part of the task. And how to create this line is very easy. I go back to the software, go to the stage, and let's go back to our selection, remove those type of selection. Look at all materials like here. Those who are not passing are shown by gray line. And now in order to draw a line with a certain slope, I select on the line. I can change the slope that I care about based on this task is E over density. So the slope is 1. do you want to maximize this or minimize? So I select maximize, and then I have an option to select anywhere in the graph. So I put it here. Now, of course, anything below this one is below this line is minimizing the index, and any material above this one is maximizing. Of course, remember that we also have these two conditions. That's why some of the materials above or beyond this line are still gray. You see, by choosing this line, moving it upwards, more material are out from our list. And by going downward, of course, more material is added. All the materials along this line, they have the same value of E over rho. So this is the short tutorial about steps from the first task that we are asked, and now we go to the next step.
Okay, so tadi dia tunjukkan menggunakan CS sebenarnya you boleh tengoklah dalam YouTube banyak dia punya tutorial untuk CS.
So this is the
cuma yang ni
short
kejap
tutorial
tadi.
About downward.
Dalam CS dia tak semestinya ada 2 stage je. Dia tak semestinya ada 3 stage. Dia boleh banyak stage lah. Maksudnya you boleh maksudnya mungkin yang stage pertama ni yang modulus versus density. Lepas tu stage kedua you nak elasticity versus density. And then you select lah. Ikutlah aturan dia. Daripada stage pertama tu, you dah select. Okay, daripada 100, bila stage pertama, mungkin dia jadi 50 saja. Kan, lepas tu you pergi pada stage kedua. You ambil elastic versus density pula, ataupun price versus density ke kan. So that result ni makin lama akan berkurang lah. Mungkin daripada stage pertama tadi, ada 50 saja material yang pas. Yang pas the requirement of the yang modulus versus density. And then you pergi pada stage kedua, mungkin price. You nak tengok price yang paling murah kan, price versus density kan. So daripada stage kedua, price tu pula mungkin daripada 50 yang pas mungkin 20 saja. Lepas tu you pergi pada stage ketiga, mungkin stage ketiga tadi you ambil by limit ke ataupun by 3 ke kan. And then at last kali, contoh dalam ni, last kali dia dapat berapa?
So this is the short all the
perimeter index ni. Okey, contoh ni last kali dia dapat 18. Maksudnya yang meet the requirement stage 1 stage 2 technical ceramic ataupun metal and alloy. Jadi daripada technical ceramic metal and alloy ni macam mana you nak pilih? Dekat sinilah yang nanti you kena pilih sama ada you balik pada objektif, sama ada you nak lightest ke, you nak you nak yang paling murah ke. You tengoklah dekat sini. Nanti dia kat sinilah ni dia rankkan by alphabetic. Sebenarnya nanti kalau you klik dekat sini, dekat rank by ni dia adalah rank by cost, by price. Rank by by yang modulus. Nanti you tengoklah rank yang mana. You nak pilih ataupun kalau you nak lagi comprehensive punya selection, you menggunakan push method. Ataupun weight decision metric mana-mana lah yang you dah pernah belajar untuk you select the best material.
Let's
Okay. So sekarang kita pergi pada engineering dan juga BOM. BOM adalah bill of materials. Engineering drawing ni saya tak adalah tekankan sangat. Sebab semua benda you dah belajar. So that the historical goal of the detail design has dia punya goal untuk detail design adalah produce the drawings. That content the information needed to manufacture the product. Maksudnya bila you dah habis semua you punya stage design tu, the final step is engineering drawing, because that engineering drawing is contain all the information that the manufacturing engineer needs. Maksudnya all the yang you design tadi you kena lukis dalam engineering design, ada bill of material semua, ada dalam engineering drawing tu adalah part yang ni material apa, berapa size, lengkap lah. Maksudnya bill of material ni sebenarnya benda yang lengkap lah. Maksudnya parts tu material dia apa, berapa quantity you nak, and then berapa size, dimension semua dia dah kena ada, sebab engineering design drawing tu lah nanti yang you akan bagi pada manufacturing. engineer untuk dia produce the product. Sebab you adalah design engineer. And then bila dah lengkap engineering drawing tadi, you pergi kepada manufacturing engineer pula. That's why dia punya ultimate untuk design product ni adalah engineering drawing. The information on the detailed drawing includes the standard view of orthogonal projection. Macam biasalah, ada the top, front, side view. And then auxiliary view, such as the section, enlarged view, semua kena ada lah. And then dimension, of course, kena ada. Biasanya dimension ni kita according to the geometric dimensioning and tolerance lah, standard ISI. And then kena ada tolerance, and then kena ada material specification and any special processing instruction, and then manufacturing details such as the parting line location, draft angle, surface finish, whatever it is. Dalam engineering drawing, dia kena complete. So that the last kali, you kena ada engineering drawing yang complete. And then the BOM ataupun bill of material is the complete list of all the items that are required to build the product. Macam tadi cakap lah, BOM tu dia ada apakah materialnya apa, berapa dimension, berapa quantity. It includes all alternative and substitute part numbers and part contained in the drawing notes. Every line of the BOM includes the product code, part number, part name, part revision, description, quantity, unit of measure, size, length, width, and specification or features of the product. Ni adalah contoh detail design drawing of a lever. Ni adalah the top, apa kata, side, top dengan dia ada apa tadi? Side, top, lagi apa? Lupa dah. Front. Ni sebenarnya dia punya bill of materials lah. Ni contoh continuous satu lagi. Ni adalah explorer drawing. Ni dia punya bill of material lah. Ini. Ni contoh bill of material. Bill of material sama ada you buat separate ataupun you boleh letak dalam dia punya engineering drawing. Ini contoh adalah bill of material untuk engine program. Ni untuk apa ni? Example of bill of material untuk dia part list lah. Sini adalah engine ni. Dia ada connecting road semua ni. Dia ada part numbers. You kena lengkap lah bill of material sebab you nak kena bagi pada manufacturing process. Manufacturing engineer. Ni contoh lagi. Okay, sekarang kita pergi pada cost evaluation. Macam saya kata lah, cost evaluation adalah penting sebab semua cost evaluation dia ada total cost, dia ada recurring cost, dia ada non-recurring cost, dia ada apa kata constant cost macam bil elektrik, bil api semua tu Semua cost yang ada tu, you kena include, you kena evaluate, and then daripada cost evaluation tu lah yang nanti you akan dapat you punya selling price. Dia bukan orang yang company ni bukan sesaja je dia letak dia dah design plan ni, dia letak RM2. Tak Dia ada dia punya cost evaluation. Dia dah consider semua cost, and then dia tengok dia punya breakdown point breakdown dia berapa selling cost yang dia perlu jual. Dan berapa profit yang akan dapat. So that kita akan tengok video ni macam mana. Video ni daripada pensyarah pada UiTM, Dr. saya tengok Dr. apa? Dr. Asri kot. And then dia akan tunjuk video ni adalah 15 minit ke 16 minit. Dia akan tunjukkan lah cara what is the cost evaluation and then macam mana kita nak kira selling price daripada cost evaluation dan juga how much the profit yang kita dapat daripada kita punya produk. Biasanya cost evaluation ni adalah the last step lah selepas engineering drawing tadi. Okay.
Assalamualaikum and good day. In this video, we will cover on Chapter 6, Cost Evaluation. At the end of this session, students should be able to understand and identify the aspect and fundamental of costing analysis. And secondly, understand and utilize the costing approach and method in dealing with engineering design project. There are two parts of content in this chapter. The first one is on fundamentals of costing evaluation, and the second one is on method of developing cost estimation. So for the fundamental, we must know what it is meant by cost. So cost is monetary valuation in dealing with the aspect of material, good or services, risk issues, resources, and etc. It means that whatever that use money to produce our product or to market it, it is under cost. So what is costing evaluation? It is a process of determining how resources are being utilized based on cost allocation and benefit. So why we need to do costing evaluation? So the importance of costing evaluation is basis for identification for product selling price, basis for identification for product profit projection, right? So from all the costs that involve in producing and also in marketing of the product will be calculated so that we know what is the selling price for our product and also how much profit that we can gain from our product. There are 4 types of costs. The first one is fixed costs. The second one is non-recurring costs. The third one is variable costs. And the fourth one is recurring costs. When we talk about fixed costs, it is a constant independent of the output or activity level. The annual cost of property tax for a production facility is a fixed cost. The fixed cost is independent of the production level and number of employees. It means that any cost that occurs that did not depend on our production or on our output will be classified as fixed costs. The second one, we have non-recurring costs. For non-recurring costs is one that occurs at irregular interval and is not generally anticipated. The cost to replace a company vehicle damaged beyond repair in an accident is example of non-recurring costs. After that, we have a variable cost. It does depend on the output or activity level. It means that if the output is more, then the variable cost increase. For example, the raw material cost for production facility is a variable cost because it varies directly with the level of production. Increase in production will also increase in raw material cost. Last but not least, we have recurring costs. It is one that occurs at regular interval and is anticipated. For example, the cost to provide electricity to a production facility is a recurring cost. Now let's take a look on the difference of non-recurring costs and recurring costs. An example of non-recurring cost is capital cost. So for non-recurring cost or capital cost, it is one-time expense only. For example, we pay for the building or the factory and maybe payment for the land to make the factory, for example. Another example is on development, investment, and other costs that are paid only once. And then for recurring costs, it is focusing on operation costs. It is repetitive, direct or indirect, which vary depending on the production. Recurring costs usually occurs daily or weekly or monthly. So in this slide, it shows us the difference between fixed costs and variable costs. For fixed costs, it is the cost associated with your business product that must be paid regardless of how much you sell. For example, rent for office space or storefront. Another example is weekly payroll and also equipment depreciation. Otherwise, for variable cost, it is the cost directly related to the sales volume of your business. For example, delivery or shipping charge. With increase of your production, it will also increase in delivery or shipping charge. And then sales commissions and also advertising and publicity. Under fixed cost, we have unchanged cost of production rate. For example, on investment cost, we have insurance and property tax, and also on overhead costs, for example, on rental or utilities bill. Both of these costs we pay either monthly or weekly. It is already fixed. And there are some that we pay annually, for example, on insurance and property tax. And then for variable cost, it is change cost of production rate. For example, cost of material will change with the production rate. And then direct labor cost, maintenance costs, and also packaging costs. All these costs change according to production. Why we learn on cost? It is because we need to develop cost estimation. The cost estimation is important for product pricing. So what is product pricing? It is product selling price that simultaneously and positively affect the customer interest and greatest profit generation. So one of the best methods to identify the price of product or services is by implementation of break-even chart. Break-even chart shows and portrays the profit and loss on the selling price of the product, and also price and manufacturing cost of product. This is the example of break-even chart. This chart will tell us where the break-even point will occur. So how to produce break-even chart so that we can do analysis? The first thing that we need to do, we need to determine the variable cost per product. For example, over here, the variable cost where we plot depending on unit sold. For example, if only 1 unit, how much will it cost? And then for 3 units, how much will it cost? And also, for example, 6 units, how much will it cost for variable cost? Variable cost includes material, labor, and purchase part. That's why with increase of units, it's also increase in variable cost. Then we need to determine the fixed cost. Over here we can see we have fixed cost. Fixed cost does not depend on the number of production or the number of sales. It doesn't matter along all this line, even the unit sold is increased, the fixed cost is maintained. After that, we need to draw the total cost as a function of the number of products on the chart. So the total cost is over here. The total cost is fixed cost plus variable cost. So we need to add up at every point. For example, for 3 units sold, we add variable cost over here with fixed cost. So we will get 1 point. So we mark that as our total cost. We should also do for all units sold. For example, for 6 units sold, we calculate fixed cost plus with variable cost. So it will show our total cost over here. And then we make a straight line as our total cost line. After that, we need to determine a sale price of the product. The sale price we denote as total revenue, and then draw the sale as a function of the number of the product on the chart. So the price will times with the number of units sold, and then we mark and we get the total revenue. So the intersection of the sales line with the total price is break-even point. Let us watch this video on how to build break-even chart.
Welcome. In this video, I'll be constructing a break-even chart using the given information. First, we find the break-even point in units by dividing the fixed cost by the contribution margin, and that gives 45. The break-even point in dollars can now be found by calculating total revenue at break-even, and that gives 2,700. To construct the graph, we plot units on the horizontal axis and dollars on the vertical. Now, suppose for units, we have a capacity of, say, 110, then we can go as far as maybe 120, as far as we capture the break-even unit of 45 centrally. And for dollars, I can do 1,000 per unit here to ensure the break-even dollars of 2,700 is captured. So the break-even point here is 45 and 2,700. Now the fixed cost is the same for any volume of production, so we draw a horizontal line for fixed cost here at 1575. For the total revenue function, we know that if we sell 0 units, total revenue will be 0. So total revenue line is satisfied by 0, 0, and we pass through the break-even point. For total cost, when 0 units is purchased, then total cost equals fixed cost. So the total cost line will start at fixed cost here and pass through the break-even point. Now, before breaking even, the total cost is higher than total revenue. So this region here constitutes losses. And after breaking even, total revenue is greater than total cost. So this region constitutes profit. And that's it. Thanks for watching.
That's all for this video. I hope you can understand on cost and pricing.
Okay. So that this is the break-even chart. So that daripada
We draw a
break-even
hard
chart ni lah,
zero.
kita akan
So
dapat tahu lah maksudnya,
the total cost is
contoh dalam
higher
chart ni,
than total revenue. So this region here constitutes cost.
okay, contoh
So
dalam
this
chart yang dia
region
tunjuk ni,
constitutes.
That's all for this video.
So this region constitutes.
maksudnya dia punya barang you kena jual lebih daripada 45 unit baru you dapat untung. Kalau bawah daripada 45 unit, you loss lah maksudnya. Inilah macam mana cara dia determine the selling price. Misalnya sebelum you buat, you kena estimate lah berapa selling price yang you nak. Maksudnya selepas you dah lukis ni semua, maksudnya selepas you dah lukis, okay ni selepas you dah determine semua variable cost, how much the fixed cost, and then how much the total cost, and then you draw the line. You draw the line for the total revenue. Maksudnya you kena pandai lah. You tengoklah macam mana you punya draw. Kalau katalah you draw line macam ni, dia macam nak macam ni kan. Maksudnya loss awak akan sikit lah. You punya profit akan banyak lah. Tapi tengoklah kalau terlalu mahal pun, orang tak nak beli juga kan. Whatever it is, this is the break even point. Break even point maksudnya point antara profit dan juga loss. Biasanya yang loss ni sikit lah. Dekat profit ni yang banyak. Kalau katalah loss ni banyak, maksudnya orang rugi lah. This is the you punya break even point lah. Berapa unit yang you nak jual baru you dapat profit. Okay, setakat tu saja kita punya kuliah pada hari ini. So that untuk besok punya activities, saya nak tengok yang apa nama tu? Human factors. Saya nak setiap group bentang dia punya human factors tu. And then dalam besok ataupun petang ni saya akan bagi untuk presentation guideline ataupun presentation punya rubrik untuk yang embodiment design punya rubrik. Sebab sepatutnya minggu depan kita akan buat presentation. Saya check. Saya akan bagi rubrik lah. Saya check. Okay, sepatutnya sepatutnya presentation sepatutnya minggu depan. Minggu depan adalah presentation preliminary design. Okay, saya rasa minggu depan kita buat presentation je lah. Untuk yang tengok macam mana dia punya, sebab minggu depan kita dah ada satu lagi chapter saja, chapter 5, chapter 4 kita dah habis. Jadi minggu depan sepatutnya presentation lah. Mungkin kita buat tak apa, presentation kita buat Selasa. Maksudnya setiap group ada masa dalam 20 minit, kita buat dalam 2 jam, ada 20 minit, setiap group 20 minit location. Maksudnya awak kena betul-betulkan lah dia punya presentation tu, time dia 15 minit untuk presentation, 5 minit saja untuk kita macam discussion lah. Nanti petang ni saya akan bagi dia punya rubrik pemakahan. You tengoklah rubrik pemakahan tu macam mana. Jadi besok saya nak tengok you punya economics lah, you punya human factors punya tu macam mana. So ada apa-apa persoalan tak? Okay, kalau tak ada, Assalamualaikum warahmatullahi wabarakatuh. Okay, thank you.
Waalaikumsalam. Thank you, sir. Thank you, sir.
Bye.